Hello, everyone, and thank you for joining us for our first session in the AIA California Monterey Design Conference University. My name is Liz Rainieri, FAIA, a member of the AIA California's Monterey Design Conference Planning Committee, and I'll be your moderator for today's segment, Accelerating the Path to Zero with Prefabrication. This morning's presentation is brought to you by Clark Pacific, a legacy partner of the 2021 Monterey Design Conference. It's not too late to join us for our first MDC on the road, coming to you wherever you are. This virtual format is our way of inviting you to see what makes the Monterey Design Conference the architect's retreat and why we have so many loyal attendees. Our headliner speakers this year will join us from Portugal, Japan, England, Boston, and of course, California. Clear your calendar, October 21st and 22nd, and carve out time to focus on these amazing architects and how their work is shaping the world. More details on this incredible lineup of speakers and registration are available online at montereydesignconference.org. A few quick housekeeping reminders before we get started with today's presentation. Please use the Q&A function to ask any question for today's presenters. You can also like a question to move it to the top of the queue. Today's session qualifies for one AIA learning unit for those watching live. AIA staff will report your attendance for you. The session is also being recorded and will be posted on the AIA California website shortly after the presentation. Now on to today's session. As recently as 10 years ago, sustainable buildings were viewed as experimental, but today are becoming more feasible. And still, owners and project stakeholders are often forced to choose between sustainability and cost. An owner may have ambitious sustainability goals, but if the cost of bringing them to life is too high, they may be out of reach. Designers, engineers, and contractors work to accommodate an owner's environmental goals, but run into problems when pricing comes into play. Often, the green features push the project over budget, and realizing the building can't generate enough revenue to satisfy the pro forma. The owner asks the team to come up with a less costly option. In doing so, green features are cut one by one until the project is within budget, but far less sustainable. Through advances in technology and innovative approaches to construction, sustainable buildings today don't have to cost more. Beginning in the earliest design phase, all the way to operations, sustainable buildings are becoming a reality without breaking the bank. I would like to quickly introduce today's presenters before getting into this program. John Mole is a senior project manager, structural engineer, and obsessively curious about the world around us. Passionate about the built environment and sustainability, Mole believes that the biggest opportunities for change lie carefully hidden in the gaps between traditional roles. To truly effect change, products must be driven toward a simple elegance by passion, hard work, and iteration. Outside work, John enjoys wakeboarding on the Sacramento River with family and friends. Doug Bevier is a project manager for Clark Pacific, helps to drive the products department and create the vision for the burgeoning and highly successful facades division. Doug has worked for Clark Pacific in different capacities since starting as a plant laborer in 2006. He became a field erector in 2010, and then joined the project management ranks in 2014 before moving to his current role in 2020. Additionally, Doug manages the Clark Pacific Foundation, which is a charity that provides support to the Yolo, Sacramento, Ontario, and Adelanto communities. Now take it away, John and Doug.
Hey, thank you for the introduction, Liz. Happy to be here. This looks like a great event. We're excited to be part of it. So the building industry has a carbon problem. Okay, I'm going to go through this quick. A lot of you guys have seen this before. Built environment accounts for 38% of the global carbon emissions. So this is the building operations and the construction and manufacturing of things that go into buildings. So, but what you're starting to see is that green isn't actually just, green is necessary, right? We need to lower our global warming potential if we want to achieve our goals by 2030 of keeping us from gaining more than a degree and a half of temperature rise. But green's also good for owners. So this is a recent study that was done by Cushman and Wakefield. It shows that LEED buildings actually have a higher rent, and they used to be more difficult to rent out. They would have a higher vacancy rate. But over the course of the last 2 years, that has transitioned through the pandemic, that these buildings are actually more desirable. People want to stay in them. They want to go in them. So not only are these green buildings able to capture more rent, but they're also have lower vacancy rates than the non-green buildings. But today's focus is narrow. A lot of people are focused on energy. They're just focused on, you know, how much energy am I using? How much carbon is created from the energy? We're starting to see people transition where they're starting to focus on the building materials themselves, or another term for that is the embodied carbon. But to date, most of the focus has been on energy. You have these terms like zero net energy or zero net carbon buildings. And we're going to go into that, and then we're going to also look at the some of the impacts of the structure, envelope, and foundation. So the rest of the building, actually, if you imagine, most people focus on the embodied carbon. They focus on the structure, the envelope, and the foundation of the building. And those are when you look at the first initial build, those are the big items that have a lot of carbon. You think concrete, steel, things like that take a lot of carbon to produce. But what you don't often look at is you don't really consider the MEP systems and the TI build-outs. And what this is a recent, maybe not so recent, but a study that was done by the Carbon Leadership Forum. And it shows how the tenant improvements and the mechanical systems can add up over time as you have to replace those systems. And very often people replace the interiors of the building at a time interval. They're assuming 15 years here. Market trends are actually trending to do TIs more often than 15 years now, probably closer to 5 to 10. But you can see that by the end of the building's life, that stuff can add up to quite a bit. And another item that often isn't thought about is energy alone can lead to bad outcomes. So this is an image of a VRF system. So a VRF system has very good energy performance. Very, it's an all electric system, so it's not using natural gas or anything like that. So its carbon profile is a lot lower. It's very energy efficient. Again, so it reduces carbon and reduces the impact. But what it also does is it also uses refrigerant as a means of transmitting the thermal energy through the building. So when you're looking at energy alone, this looks like a great system. But when you're looking at global warming potential, the refrigerant leakage that can occur over the life of this structure can be almost as much as the energy that's used by this to create the heat and cool to make your building comfortable. So we need to take a bigger look at these pictures. We can't just focus on the energy alone. So luckily there's a more complete picture out there and it's available. This is a carbon life cycle assessment or whole life carbon analysis. So this is where you look at the carbon from every phase of the building, from product stage of product material extraction, all the way through the use stage, including the end of life stage. A lot of people like to focus on one, like the energy, or they like to focus on the other, which is like product stage, primarily because they shine in that area. But they don't have much, they try to not talk about the areas they don't shine in, if that makes sense. So we just need to make sure we're looking at the whole picture. So with that, we need to rethink how we build. So this is a process that I've been through. It's happened to me a couple of years ago as I was going through this building and we were going through a design build process. And we were talking about, the owner had these ambitious goals of being very sustainable, very energy efficient. And we went through the whole thing with the conceptual design, the schematic design, and all the way through this, we're coming up with these great ideas. We're trying to solve this problem. We're trying to, as a team, enact the vision. And as we go through this, at certain checkpoints, we're doing cost estimates. And at some point, towards the end of it, the cost for these items that we're implementing became too high. And the developers stepped in and said, hey, whoa, my performance is not working. We need to cut back. We need to trim. And so you ask, okay, well, what programming do we want to get rid of? Well, the programming is tied to the proforma. We can't get rid of any programming. So the only thing you're left is all these sustainable features that were in their original desire to develop. So we start cutting those back one by one until it meets proforma, and then we move on. So there must be a better way than doing this, right? And the problem is you don't have enough time over the course of a project to figure this out and get it right. I mean, you might get lucky, but most of the time you try your best and you end up where you end up, and then eventually the project needs to move on. You're tied to a schedule. So what if you could do it before you actually had to do that? So this is what we focused on. We wanted to develop a cost-effective system that achieves these low carbon goals before we got to a project. And then what if we develop a building system that actually integrates and harmonizes the mechanical with the structural and makes it all coordinated ahead of time so that we don't run into all these pitfalls that you normally run into in the building. So this is and I'm going to show you this mainly because I want to give you reference, because a lot of the examples and stuff that I'm showing you come from the building system we developed. So I just want to kind of walk you through what we've done. So we developed this net zero building platform. This was an integrated structure, mechanical, and facade. So it encompassed all of the main components of the building and the building energy system and the structure. This whole system was designed specifically to meet the 2030 challenge with carbon in mind, low embodied carbon, and operational energy as low as we could get it. So the whole thing was developed to kind of answer this question as best as we could using a system that could be applied to a commercial office building. So let's take a closer look at the embodied carbon. Okay, so using this system, and I'm going to make some bold claims here, right? We took a systematic approach to our building, and we went through it to reduce the embodied carbon. Really, I'm only focused on the embodied carbon, and I'm specifically going to focus on the concrete, because the concrete is a lot of the carbon in a concrete building, and we're precast concrete producers. So let's look into this a little bit. So where did we start? We started by taking a look at our building. We started breaking it down. And we really looked at, okay, how much volume of concrete is in each one of these components that we're looking at. So we have the floor planks, we have, there's a hollow core deck in here. So this is an example building that I put together. It was like an 8-story, 240,000 square foot building. And we broke it down by component. And this really gave us an idea, a roadmap of, okay, if we really want to take this on, we want to put a lot of focus on the big ticket items, which in this case is the foundation and the floor planks. These are the big ticket items for us. Right, so then we started digging into the materials, right? So we know what to focus on at the structure, but then we need to look at what to focus on in the materials. And the best thing to do is actually go through your mix design and understand where the carbon's coming from. So this was actually a tool that ZGF Architects created, a life cycle assessment tool, actually very handy. So I really appreciate them developing this and handing it out for free to everybody. But what you can see here is that if you take a typical 5,000 PSI mix, normal weight concrete, you can see that a majority of your impact is coming from the cement, right? This is no surprise. That's what you would expect. And then if you go to a lightweight concrete mix, you see, again, a big portion of it's coming from your cement, but you look and you see, wow, a lot of it's coming from the lightweight aggregates. What's going on there? Well, what most people don't understand is that aggregates are mined and crushed and delivered, but they're not, lightweight aggregates are a little bit different. A lot of those are manufactured. They put them through a kiln, they're heated up to like 1200 degrees Celsius, and it makes the aggregate actually expand. And that whole process adds, as you can see, a ton of energy to it. Now, there are alternatives that you can use volcanic sources. There's other sources as well, but you should just be conscious if you're trying to reduce carbon of what kind of aggregates you're actually putting in your concrete. So the approach today, what's mainstream, is what we call cement replacement. If Portland cement is the high carbon element in concrete, then you want to take as much of that as you can out and you want to replace it with something. So what we're replacing with today are supplementary cementitious materials. These are things like fly ash, slag, silica fume, those type of items. And I've seen approaches that can get you anywhere from 70 to 80% cement replacement. The trade-off is you lose strength gain as you're doing that. So you get lower early strength. You tend to get higher long-term strength though. All right, so this is our product-based carbon reduction. So this is taking one of the components of our building. Remember I said the floor system is one of the largest items in our building and with most buildings, right? So we looked at it, we said, okay, it has a high impact potential. It's 35% of the structural concrete. We want to set some goals. We want to have 70% cement reduction. That is achievable. Again, it affects your early strength. We need 3,500 PSI overnight. So now that's a pretty high early strength. So those two are in direct conflict, but hey, we're reaching for the world, right? We want our slabs to actually be thinner than concrete over metal deck. So we made these slabs 4.5 inches thick. So we put all these initiatives together. How do we make this work? So first of all, we leverage the shape to reduce the volume of the concrete. So you notice this isn't just a two-way flat deck like cast in place might do. This is a system with shape to it that looks more like a steel building so that it can more efficiently use the materials. Then we went to a pre-top system because precast is normally topped. By pre-topping it, we're able to actually cut out about 2 inches of thickness from the concrete over the entire building, which is huge. The next thing we did, because again, I wanted to make these slabs really thin, we actually had to get UL fire testing because it's not rated to be less than 5 inches for a 2-hour fire rating. So we went out, we developed a specialty mix. We got our UL for a 2-hour fire rating on a 4.5-inch slab. So all these things added up to reduce the volume of concrete that we're using. And then the last thing we did is we actually, because we're offsite fabricators, we added heat to our forms. So by heating our forms, we're able to get our overnight strengths of 3,500 PSI with a 70% replacement mix. So that is huge, right? That's something that you can't normally do out in the field because that same mix would get about 500 PSI without the heat. So it would take them like several weeks before they could move to the next floor or things like that. And then just a lot of people ask this. So the form heating allows us to go from say a 35% replacement mix to a 70% replacement mix. This removes about 110 kilograms of CO2 per cubic yard. And then the heat adds back, let's say about 12 kilograms per cubic yard. You don't get the heat for free. Although we do have on-site solar, so the 12 is probably less than 12. It's probably closer to 6 for us. Okay, so backing up my earlier claims, just real quick. So we took 23% less concrete and 47% less CO2 in the mix from the high cement replacement. And that gave us an overall of say 46 kilograms of CO2 per meter squared reduction on the building, which is what I'm saying 70% of the CO2 is removed from the concrete. That's 46 is actually a really big number. That's, our whole building is somewhere around 180 for the structure, facade, and core. And so 46 is actually a pretty significant chunk we took out of that. All right, I'm going to hand it off to Doug.
Awesome, thanks, John. As mentioned earlier, my name is Doug Beer. I'm the product manager for our facades product vertical here at Car Pacific. Before I jump in, I just immediately into our carbon story. I just wanted to quickly highlight what product we're referencing for the cladding system. It's a pre-designed integrated weather barrier system. It consists of a metal frame that carries all the loads back to the structure, a thin concrete or GFRC skin, a factory installed insulation and windows. Really what we try to do here is just bridge the gap between utility and aesthetics. The layout and the articulation of the panels can be highly customized from glazing ratios to multiple opaque infill options. And so what we did as far as the embodied carbon discussion is we first engaged Walter P. Moore and Associates to help perform a life cycle assessment, not on the building as a whole, but just we really had them focus on our system components. So we looked at our infinite facade panel system, which is what we call it, and to understand the global warming potential per square foot of each of our potential configurations, to really understand the impacts of the different variables within the infinite facade system and how it compares to other common wall assemblies. And then we conducted a handful of different separate LCAs using the Tally software plug-in through Revit. So John referenced some of this earlier in his discussion, but I put these graphs together. So we measured global warming potential based on gases to CO2 equivalent. So if we look at the pie charts that I'm showing, we will see components, which components of the wall assembly have the largest impacts. And we also wanted to compare it to overall mass for the components to see what, if any, of the materials had an outsized impact based on their mass percentage. So really what I wanted to point out here on the right-hand side is that, John referenced it, but most of the impact we see in the concrete is due to the Portland cement. So it's roughly 20% of the mass, or 21.3% of the mass, but it accounts for well over 70% of the global warming potential in the concrete or GFRC skin. So with this wall system design, we immediately attack the embodied carbon versus traditional architectural precast concrete components by reducing just the concrete volume required. So we really just wanted to leverage the shape, and rather than utilizing a 5 to 6 inch or sometimes greater than that thick concrete panel, we removed well over 60% of the Portland cement content by moving to a 2¼ inch concrete skin or a 1 inch GFRC skin. In addition, this helped to reducing just the embodied carbon within our concrete assembly, moving to this type of system versus traditional, we call it APC for architectural precast concrete. We lessened the demand for the supporting structure by over 50%, right? So that's going to have some downstream effects as well. I also wanted to speak about the insulation for a second and discuss what we've recently investigated and kind of changed our system towards. So through this Tally analysis, we really got to hone in on what type of insulation we were going to use for the wall assembly. So to meet or exceed our continuous insulation requirements, we use a high R, it's roughly 7.4 per inch, spray foam insulation. I understand spray foam can be a bit of a trigger word, so I wanted to emphasize that we're taking steps to reduce the impacts and the effects of the spray foam. So the industry has changed from an HFC to an HFO, which has dramatically decreased the carbon footprint impacts, which is what I'm trying to show on the screen. And so what you're going to actually see here is that we were able to reduce about 2.2 carbon equivalent per square foot. Really, it was a reduction of 23.4% of our original system. The factory installed insulation helps us maintain a controlled environment, which increases the quality of the control of the application of the spray foam itself. And so then we thought, okay, well, where do we go next? It's the obvious answer. Well, it's got to be the cement content. And so reducing the volume needed was just the first step. So John kind of discussed the current ways we've replaced cement content in mixes with SCMs. And so we've done a lot of research and testing and developed a proprietary architectural mix that currently replaces 35% of the cement content. I think some of the biggest challenges facades sees versus structure is just maintaining the color ranges and consistency that architects or the client wants to see in their facade systems. Historically, across the industry, this has been a challenge for most filler alternatives, but we figured it out. We're continuing to research this and hope to continue reducing our content to well over 50% in the future, utilizing some of the strategies John mentioned with heated forms and just more investigation with different types of SCMs. So what I wanted to show here on the screen is just the impact, right? So we're going from a 7.12 in our lowest standard mix, a 7.48 in our highest standard mix, down to a 5.9 for the system, right? So really reducing our cement content in the skin helped us reduce about 18% in the overall system's carbon per square foot. So what does this all mean? Now, I had to continue to educate myself and utilized Walter B. Moore to study several other types of wall assemblies, just to kind of understand where do we stack up in the industry, and are we competitive? And so as we looked at different curtain wall systems that had published DPTs, we looked at ACM rain screen wall assemblies with enough insulation to have the same thermal performance of the infinite facade. And we found out, we were in line or lower than, or had lower global warming potential than all these other systems. And that's what I was trying to show on the graph, is that although concrete can be a trigger word, we stack up really well against glazed curtain wall and metal panel assemblies. We also looked at different window to wall ratios along with our system, and you can see how that stacks up as well on the graph to the right. And then I just wanted to move on. It's a double-edged sword, right? It's operational and embodied carbon. So I wanted to talk about some of our system's performance and the operational carbon side of things. So in addition to Walter B. Moore, we contacted GluMac, and we worked with them on a parametric energy analysis on several envelope systems and compared them to the infinite facade. We touched on multiple different variables such as window to wall ratio, different climate zones, envelope systems. Really just wanted to see how our system compares in regards to energy and greenhouse gas emissions to other systems, and how much insulation is appropriate for any kind of given climate zone. So really our study looked at two different building types, high-rise residential, and then as well as commercial office buildings, which is works with the net zero platform. Our typical high-rise residential building used a case study, 24 stories, ground floor retail, rooftop amenities, underground and podium parking, central corridor, and an approximate window to wall ratio of 20%. We also looked at a typical office building. It was 6 stories. It was about 200 square foot corn shell. And then the HVAC systems we modeled were after the ASHRA 90.1 Appendix G system type, and is representative for the typical HVAC systems for office and residential buildings of this size. Then we held all that constant across 4 different geographic locations here on the West Coast: Sacramento, San Francisco, LA, and Seattle. And then we also looked at 3 different window to wall ratios in typical ranges that we see in our market, so 40, 55, and 70. For our infinite facade system, when under full thermal performance modeling, the 3 structure of the wall assembly, including the structure of the system, attachments of the facade back to the structure, concrete panel back to the structural frame of the panel, and really gave us a good understanding on how the system would perform upon installation. So the envelope options that we looked at, in addition to our typical infinite facade system with 2 and 3 inches of insulation, was that we looked at the Title 24 baseline. We also looked at the Seattle Energy Code. We looked at typical curtain wall and Title 24 compliant metal frame walls. So our 2-inch system had a U value of 0.065, which is right around the Title 24 baseline, and a 3 inches of insulation had a U value of 0.046, which exceeds both energy codes. So here, I just wanted to show I'm going to go through just some of the highlights of the study and kind of some of the insights we gained through this. So this shows the infinite facade with 2 inches of continuous insulation. Really, I just wanted to show this to show that there's just a really wide variety of energy usage depending on the climate zone, the building type. For example, a residential building operates 24/7 versus an office building, and you can see it has higher energy usage. We do not have time to kind of go over all of the extensive results, but rather I'm going to take a couple different case studies and speak towards that. So here we're looking at a window to wall ratio and how it impacts the performance of the building. So what we found was fairly consistent across all climate zones. For about every 10% increase in window to wall ratio, you'll see about a 5 to 7% additional annual energy usage. And that's consistent in heating and cooling climates, such as the Seattle region we studied and LA. So now I just wanted to highlight one of the case examples. So we looked at an office building in LA with a window to wall ratio of 55%. So starting with Title 24 and looking at typical curtain wall with R13 infill, you will see an increase of 19% energy usage. We're looking at buildings and comparing them to increasingly more difficult energy codes to comply with, starting with like a typical curtain wall system will really put the building at a disadvantage just due to the cooling and heating loads. Then we looked at the infinite facade system and noted an increase, half of that of curtain wall. So you'll notice about a 1% difference in LA between 2 inches and 3 inches of insulation. So there was just a diminishing marginal return. And then we compared that back to the embodied carbon of that insulation and realized, that the diminishing return didn't outweigh the additional global warming potential. So it's just another way of utilizing this information to make the best choices for our built environment. Looking at greenhouse emissions over time, the infinite facade system used released about 12% less emissions than that of curtain wall. Upon request, I can send out the full report, which dives into more case examples and extensive more research. And then I just also wanted to point out that although we didn't incorporate this into the study, we also utilize and can utilize the aesthetic design to help control UV rays and energy performance on a building. So this was a project we did in San Francisco, and the photos on the right are the same building, just different elevations. One had these large billows, which is in the top photo, in locations where there was really high sun exposure versus elevations at low exposures, which we used a much simpler and flatter panel. And the reason we did this was to meet the proforma and help use economical choices on the lower impact regions and really spent the money where it mattered on the highest impact locations. So it's just I just highlighted this because it's a great example of aesthetics and performance working hand in hand. I'm going to hand it back to John to talk about the integrated system.
Hey, thanks, Doug. Always love seeing all the cool things that we do throughout the company. So it's fun seeing it. So I'm going to shift back to structures now. Again, looking at our structural system, I just kind of want to set everybody. This is kind of the whatever 30,000 foot view shot of what the structural system looks like. It uses rib floor planks, and then it also has facade system around the outside. It's got the full structural core for lateral and things like that. So the this whole perimeter of the building uses what we're calling a thermally active deck. So this is radiant heating and cooling, which is a very efficient way to heat and cool a building, and a very comfortable way to heat and cool a building. The thing is this system is often associated with higher cost when we're talking about field construction. But when we move that work off site, it actually flips the equation a little bit. Now all of a sudden you're getting this really high efficiency, high performance system, and it can actually be a cost benefit to the project. So this is in a nutshell what these panels look like. They've got in-slab radiant manufactured in a single process. The same guys that are tying the reinforcing are actually placing this in the plant. It's got inner control zone and an outer control zone, so you can treat the perimeter of the building where the environmental energy is coming in through the windows. You can treat that separately from the interior of the building, where you've got mostly computers and people drawing heat into the building. It's got integrated offsite fabricated hydronic system. So a lot of the plumbing and controls and even the control logic is all controlled and assembled onto the panel. It's almost like this is a structural unit that's an HVAC panel that's shipped out to the site complete. And then these are just interconnected out in the field. So we've done as much as we can to really make this system as efficiently delivered as we can, and as well as efficiently operated as we can. For instance, the research that has gone into the control sequences and things like that in order to optimize and best leverage the thermal mass of the structure for the lowest energy. So putting it all together, when you put this floor system together in a structure, you end up with something that looks like this. And I know I'm showing I'm showing a very open office, but what we do with closed offices, or if we have a conference room or something like that, then we directly pipe air into that room and then it's on a demand control system. And so we make up for the, for the occupancy, a high occupancy area by pushing more air into that room, which is, actually feels better if you're in the room because you're getting more fresh air. So this system uses 100% outside air, fresh outside air when it's coming in. Most of the space heating and cooling is taken care of by the radiant, either heating or cooling the slabs where appropriate. And then one of the things that we found is that the energy efficiency of actually moving air movement is comfortable. If you're outside and there's a gentle breeze, it's a lot more comfortable than it's just stagnant, right? And so the same thing would apply to an indoor environment. So we put these ceiling fans in to run the air and just have a little bit of background movement. We actually run them in reverse. Not only does that enhance the performance of the slab itself, but it makes the occupants feel a little more comfortable. And in fact, the occupants have control over the fans. They can go over and turn it up, turn it down, reverse it, whatever they want to do to enhance their comfort. Say they just got back from a jog and they're feeling a little hot, they can turn a fan on. And then the other thing you'll notice is just because it's a radiant ceiling doesn't mean that you have to have the entire thing exposed. An office building needs to have acoustic performance. So we found that with these strategies, you can get about 60 to 70% coverage with an acoustic treatment of ceilings, as long as you leave, some gaps in between. So like a cloud-based, like isolated cloud ceilings are awesome for this. And you want to have a little more exposure on the perimeter where it's working a little harder is the key. And then I just want to make a note, right? Inefficient systems are also very forgiving because when you have an inefficient system, you're basically just blasting energy out of it, right? When you get into these high efficiency systems, they require a little bit more thought, a little more of a symbiotic relationship with items like the facade or the ceiling. You've got to do a little more thought around it. So for instance, in this one, a radiant system has limited capacity. That means you have to control how much energy is being hit at one time, which is why I said, okay, we're pushing air into the conference rooms. But the same would apply to the perimeter of the building. So you need to put a facade system on that will support that. You can't just have direct sunlight coming in the building and hitting the floor and heating it up, or somebody's going to be uncomfortable for like an hour or two during the day, which is not acceptable. So putting in solar control or electrochromatic glass or approaches like that can really be good strategies for making the system really hum. And then if you do that, the results you get out of it are amazing. So this is what we were able to find. So we compared this against what, VRF, which is a fairly high performance all electric building system, HVAC system. And we found that with this system, and we have a study on this that you can download from our website, we reduced the total electricity usage in the building by 30%. We actually cut the HVAC energy in half, if you can imagine, of an already high efficient system. So, and it's just being thoughtful about the strategies that you're using to employ this. And a lot of people don't believe me when I say, oh, you can get half the energy from a VRF. And I try to, and this is hard to see, right? I tried to explain it using these two graphics. So the one on the left was given to me by Integral Group who performed the studies for us. This is showing heat performance curves or energy performance curves of heat pumps. And one of the ways that we're able to really enhance the energy efficiency of our system is if you can imagine if you've got a small little mechanical unit, a fan coil unit, you're going to use really hot water, like 120-degree water, or you're going to use really cold water, like 50-degree water, and you're going to blow air through it. And that hot water and that cold water in a small area is what gives you the ability to heat and cool the space. We're taking a different approach. We're using very mild temperatures. So instead of 120-degree hot water, we're using 85-degree hot water. And then we're spreading it over the entire ceiling of the structure. And the way a heat pump works is it moves heat. It doesn't create heat. And the less you have to move the heat, the smaller the distance. So from the difference between your outdoor and your indoor, the more energy efficient that system is going to be. So with these heat pump curves you're seeing on the left side there, a typical system is going to be in the range of 2 to 3.5% or coefficient of performance. That's how much heat you get out of it versus how much energy you put into it. And then if you look at our system, because it's got a milder temperature, we're all the way at the top. We're somewhere in the range of 3 to 5.5 times the coefficient performance. So you're just seeing, I don't know, something 30-something% increase in energy efficiency, 50% more efficient. And then the other thing we're doing is because we're leveraging the thermal mass of our building to our advantage. So we're actually restricting when this system can run, because we can charge this concrete slab, we can charge it with cold or heat, and it'll actually retain that. It'll hold that, and it'll hold it for 24 hours. So what we do is we push that energy into it when we want to. So we can choose when we want to use energy. So you can use it during low rate times, or you can use it when you're generating PV. Any of that type of approaches works for you. And then you store it in a slab and it releases into space and maintains comfort over the day. But what the side benefit of that is when a heat pump can simultaneously create hot and cold water during the same cycle. So if you can use the hot water that's a waste product of the cold, or cold water that's a waste product of the heat, then you kind of get one of the two for free. And what we're finding is that 35% of the energy that we're generating from heating and cooling is done in a simultaneous fashion. So it's 35% of this is being done at a discount, in other words. So that's the other way that we're able to get these crazy efficiencies. So, and then when you look at the whole picture, you look at the full building. This is, again, out of that report I was mentioning. We did a whole life carbon assessment on a typical steel building with a VRF, and we compared it in parallel to this building system, which is a precast with all these features that I've been describing, with the ones that Doug was describing as well, with the infinite facade incorporated into it. I think we did about 50% infinite facade and 50% curtain wall system, just to try to make it reasonable. But you'll find that this new building system beats it out in every way. The structure is less, the mechanical embodied carbon is like half. The energy usage is like I mentioned, but quite a bit less. Even though we can't control the plug loads, the interior lighting, things like that, that wasn't part of the bounds of the study. But then one of the things you see that, you remember I mentioned the refrigerant leakage. When you look at a VRF system, look at how big the refrigerant leakage is over the life of the thing. It's almost as much as the structure itself. I mean, that's actually insane. So by using water to transmit thermal energy through the building, you can actually save a lot of CO2 or a lot of carbon equivalents. So I guess in conclusion, just rethink a little bit how you're building. Really focus on the embodied carbon. Look at the sources of the embodied carbon, and there's always strategies you can do to kind of trim around the edges on those. Leverage everything that you have. So for instance, I was leveraging the thermal mass of the structure to promote energy savings. Doug also leverages the thermal mass of the concrete to promote energy savings through the facade, or stability through the facade of thermal. And using these integrated approaches in both the facade and the structural mechanical systems can really achieve amazing results if you leverage them right.
So that concludes our presentation. So as mentioned in the beginning of the call, there's a Q&A section. It looks like we do have a couple questions already, so we'll start to go through these. Lucky me, they're both for John. There was a question here: what temperature were the forms heated overnight?
Yeah, I answered that in the chat, but we're typically heating 120 to 130 degrees Fahrenheit to achieve that 3,500 PSI overnight.
And currently on the facade side, with our mix design, where we don't have to introduce heat, that may be a solution to continue to improve the percent of replacement. And then the next question is, what type of quality control is used in the factory during installation of the radiant tubing to guarantee that there will never be any leakage in the planks? It appears that this could be permanent installation with no possibility of repairing leaks.
Well, that's okay. So a couple things. One, we do have quite a bit of quality control on these. We actually have a whole procedure where we pressure test the PEX as it's being installed into the panel and as the concrete is being cast into the panel. We also have quality assurance around the location of the PEX, because we want to make sure that locations of those PEX are tightly controlled so that we know exactly where that PEX is in the panel, so that later you can identify the location and drill. If you need to drill through the slab, you can avoid it. And we move it into the center of the panel so that things like shot pins from your metal studs can't reach it, things like that. I would disagree with your comment about saying that there's no way to repair it. We actually regularly repair it. I think one of the last office buildings we built was a Fortinet office building in Sunnyvale. There were a couple locations where some people drilled into the PEX. I think we had, I want to say 6 repairs on the job. And we sent a person out there to chip into the concrete and make those 6 repairs. And I think it took them about 2 days to make all 6 of those repairs. So leaks can be taken care of. It's not a big deal. And on the grand scheme of things, 2 days of labor is really not that much when you think about all of the work that goes into putting a building in place, right?
Yeah, and I'll just add on to that too. That's just another benefit of pre-manufacturing in a controlled environment in a plant, rather than trying to do something that fails. It's just the higher level of quality control we're able to maintain is a real benefit. And then Kathy had a follow-up question on the PEX joints regarding our standard connections and installation guides.
Develop a standard connections for the PEX. So the PEX in the slab, the part in the concrete, is uninterrupted with no connections. Once it comes out of the slab, then we've got our whole controls system that we've set up. It goes into a multi-T, it goes into the control valves, all of that stuff is plumbed off site. That does all use PEX. And then once it goes into the main distribution pipes, those would be by the mechanical contractor on the job, delivered to us, and we would tie into them in the plant. But then that scope is by them. So that would be whatever material is specified on the project, commonly copper. But you could easily go to a PEX system and you could save embodied carbon there as well on the main distribution pipes. But we currently leave that up to the designer.
That's it for the question and answer portion.
Doug, we have a few in the chat box.
Oh, awesome. Thanks. I'll flip there next. Do you want to hit the what's next first?
What's next?
These are the 2 questions.
Okay. Is there 2 or 3? I thought there was one above. Oh, no. Okay. Sorry, I'm reading. How do the costs per square foot compare for the baseline steel VRF to low carbon solution? So that's an interesting question. We're in the middle of actually doing a study on that. We've done some preliminary studies, where we're gathering information from different contractors. I think what it comes down to is we're probably about cost neutral or maybe slightly higher on a core and shell delivery. But where we really save money is on the full delivery after the TI. Because as you can imagine, on a core and shell, typically you're just stubbing the HVAC system, you're stubbing the air out into the space and you're capping it. You're stubbing the hydronic system into the space and you're capping it. With radiant system, we're actually installing all of that equipment ahead of time during the core and shell, all the radiant heating and cooling. And in fact, we're also installing all the distribution piping at that time too, because you can't just leave a building with no heating or cooling. You have to have some. So we want to hook it up and allow it to run in the background. So we're a little bit, I'd say, either cost neutral or maybe just slightly higher at the core and shell. And then because we've already installed all that stuff ahead of time, so you have tremendously fewer VRF boxes. You don't have all the reheat lines that you have to run everywhere, all the copper lines. Or the condensate collection system, none of that exists. So I'd say overall, we're probably, I don't know, I would guess in the range, somewhere a few dollars a square foot less, something like that on the overall.
And then can we discuss some of the innovations and goals we have next? I'll take that on first.
Yeah.
On the facade side, it's just continuing to leverage and optimize our current system. So obviously, we want to continue to make further improvement on our cement replacement. Yeah, that could be utilizing heated decks, it could be using curing chambers, but really just ultimately increasing the percentage of cement replacement. We're also looking at geopolymers and other types of solutions for that. We're looking at actually lightening the concrete mix design, so just continuing reduction of loads onto the structure, and And then the next step we're going to take, which I'm pretty excited about, we partnered with Haleo Glass, it's a smart glass, to help improve our window to wall ratio. So the on the higher ends, your 55, 70% window to wall ratios, we can improve energy performance utilizing smart glass, right? And also photovoltaics and the actual facade assembly itself. So that's kind of new grounds for us, and it's been an exciting adventure. John?
Yeah, for us, it's just continued refinement of our mixes, trying to, we're looking at different technologies for not only doing cement replacement, but and geopolymer concrete is one of them. And one of the other ones that we're looking at is a nanotechnology that basically squeezes more juice out of the Portland cement that you do use, which allows us to reduce the powder even more. So there's a few things that we're looking at like that. On the design side, we're continuing to look at optimization of the different components and further integration of the components. Like Doug and I have something planned where we're going to get together and talk about it, developing a better integration between the structure and facade, so that the two, can go together more closely, a little more easily, and save labor out in the field. Trying to think of what else, continuing to do energy research. Actually, one of the really interesting things that we're looking at right now is not even related to any of this, is microgrids. So when people use microgrids, you think of, okay, you've got solar, you've got a battery, and you've got a building, right? So you've got those three things working together. Well, we bring a whole nother variable to the table, and that is that your building itself can be a battery. And so we can actually leverage our building, the HVAC system itself, as part of this microgrid. So we're looking into that. There actually could be quite a bit of financial benefit to doing that as well. So, oh, there's one more I missed.
No.
Okay. So I'd say a higher upfront cost on it. So the question is, so it sounds like there's a higher upfront cost than a typical system. Did you do a payback study for energy savings over time? So we haven't done that. And I want to just be clear that it's a higher upfront cost or equal cost at core and shell. Core and shell is not an occupied building, right? That's just a structure with a facade and maybe an elevator and bathrooms, right? By the time you build out the entire building, the occupant, the tenant takes hold of the building, then I believe we're cheaper than the overall system. I don't want to make bold claims here. It depends on it depends on where we are in the market. Like, we play really well in the Bay Area. The Bay Area, we can actually be quite a bit cheaper. Other regions of California, it might be closer.
And then on the facade side, we did create a dashboard to we did go further into the energy savings over time. Compared against the systems we talked about in the BlueMax study. That'll be published on our website in the next week or so. But it's a kind of a cool dashboard just to see location, insulation type, wall assembly, and savings per year, built around some assumptions on different building case examples. And it looks like that's all the questions we've received. So I appreciate you guys spending some time with us, and we enjoyed talking about what we're doing over here at Park Pacific.
All right, thank you guys for tuning in. It was a lot of fun.
Well, a big thank you again to John, Doug, and our MDC legacy partner, Clark Pacific, for this excellent presentation. Thank you. If you've made it this far, AIA California staff will submit your attendance for AIA CE credit. It should appear on your transcript within a few weeks. AIA California will be hosting more partnered webinars all week long. Details about the 2021 MDC University are available on the AIA-CA website. Thank you again for joining us today, and we will see you at our next webinar.